Hey everyone. So in this session, we're going to continue our discussion of the Big Bang and our evidence for the Big Bang, specifically focusing on this cosmic microwave background. We've talked about the cosmological redshift, how we see galaxies all moving away from each other in a pattern characteristic of an expanding universe. We talked about the amount of hydrogen and helium that would have been produced in the early universe and how that matches the oldest gas clouds that we see. We talked about the large-scale structure formation, those timelines, and how we compare the timeline of the Big Bang with the oldest star clusters, the abundance of heavy elements that have gone through the star-gas-star cycle. But for this one, we really want to focus on this cosmic microwave background radiation. And this was really the discovery that in the scientific community put the Big Bang theory over the edge for, okay, this is our currently accepted theory, and the data and the evidence has only gotten stronger since then. So again, how do we observe this radiation left over from the Big Bang? The basic idea was during this era of nuclei, we had all of these free electrons. The universe was so hot that all the material in the universe was this hot plasma, and photons love bouncing off of these free electrons, so the universe would have been opaque. When the universe cooled down enough to actually form neutral atoms, all of those electrons would have been captured by the hydrogen and helium nuclei. No more free electrons means that photons of light can freely move through there. And we talked about this picture a little bit before, how, again, notice the timeline's kind of upside down for what we have over here. But the era of nuclei, we have all of these. Sorry, why it's doing that. At the end of the era of nuclei, the temperature of the universe would have been around 3000 Kelvin, and it would have been giving off primarily infrared light and maybe a little bit of red light as well at those particular temperatures. And that light would have scattered one more time and then freely moved through the rest of the universe as the universe became transparent. And what we see around us today, that leftover light from the Big Bang, from the transition from the era of nuclei to the era of atoms, that light is still traveling around today, but it's now in the microwave and radio part of the spectrum at a temperature of around 3 Kelvin. So again, we've kind of already talked about this during the era of nuclei and earlier. The universe contained free electrons, those scatter photons. And at this point, in this era of nuclei, the universe would have looked like a white-hot fog. Again, over 3000 Kelvin temperature. So if you were there, you'd be incinerated pretty quickly. But let's say you could be there and not be incinerated. The universe would be a dense, white-hot fog. But once the temperature drops below 3000 Kelvin, we can start getting these neutral atoms and the universe becomes transparent. And again, those photons that were bouncing around, they bounced one more time. And now, once they bounced that last time, their properties are set, and now they can travel freely through the universe pretty much unimpeded. So the original emitted light would have been, again, in the red part of the spectrum, mostly in the infrared part of the spectrum when that light was originally emitted. But we've talked about this cosmological redshift idea, how the longer ago something emitted its light, as that light is in transit, the more the universe has expanded since that point. And these wavelengths of light get stretched out along with the expansion of the universe. So since this light was emitted only 380,000 years after the Big Bang, and then the next approximately 13.8 billion years, the universe has continually been expanding since that, this light is going to be extremely redshifted. That red and infrared light that we started with would have expanded so much that now the light is in the microwave part of the spectrum, part of the which is a part of the radio part of the spectrum. So the originally emitted light, it's been traveling through the universe for so long, and the universe has expanded so much that this light is very, very redshifted by a factor of over 1,000 times the wavelength. So this light, how do we know that it actually comes from this era in the Big Bang? Well, when we have different kinds of light or different kinds of radiation, depending on where we look in the sky, that tells us about the sources of these this type of radiation. For example, if I'm looking at visible light, well, if I go outside and look around, when I look at the sun, I'm going to see a lot more visible light. So much so that it'll actually damage your eyes. You shouldn't look directly at the sun. But we can tell, oh, a lot of light comes from the sun, because when we look in that direction, we see a lot of that light. Let's say we had a type of radiation that was coming from stars in particular, different kinds of stars in particular. Well, if we looked at the night sky to try to detect this type of radiation, whatever it is, if we were looking in the disk of the Milky Way galaxy, that disk that kind of cuts across the sky, if we were seeing more of the radiation coming from that disk, we would be able to conclude, okay, stars are going to give off this type of radiation because this radiation is coming from this disk, and this disk is full of stars. When we look away from the disk, where there are not many stars, we don't see this radiation. When we look at the disk, where there are lots of these stars, we see this radiation. If there were some signal being sent by galaxies, well, we can look at different regions of the skies where there are clusters of galaxies. Some areas there are lots of galaxies. Some areas there are very few galaxies, those voids. If we see this kind of signal coming to us from the galaxy clusters and not from the voids, we can probably conclude that this light is coming to us from different galaxies. When we look at the cosmic microwave background, this CMB light, we see it coming virtually equally from all directions. So almost equal radiation from all directions. So if it's coming from us from all directions, the source of that light must be equal in all directions. And if the light was coming from these early eras in the expanding universe, this universe, when the light was originally given off, again, we're using this kind of a balloon model, that light was originally given off at all different locations in space. It wasn't focused on any individual galaxies or any individual stars. It was being given off by all the matter in the universe simultaneously at that same time. And when the entire universe became transparent, then that light is able to freely make it through space. So on this diagram, if I'm living at a certain point on this expanding universe, no matter where I am, since this light was given off early on from everywhere in the universe, no matter where I look, I will see this particular kind of radiation. So since we see this light coming almost equally at us from all directions, this implies that the source of this light is the universe as a whole. So the source is the universe as a whole. So again, no matter what direction we look at, we're going to see some region of the sky where billions of years ago, when we went from this era of nuclei to the era of atoms, that particular region had that light being emitted, and it's just now reaching us. So The properties of this cosmic microwave background, that it seems to be coming at us from all directions, suggests that it's coming from the entire universe as a whole, not from some smaller scale object inside the universe, like individual stars or individual galaxies or even galaxy clusters. It's coming from the universe as a whole. We talked about look back time, how when I look at something that's further and further away, we are seeing that object as it was further and further back in time. So as I look at objects that are more and more distant, I am seeing the universe as it was further and further in the past. Well, if we're here at our present time and we're looking further and further away, equivalently further and further back into the past, eventually we'll look so far away that we actually reach the time when this cosmic microwave background light was originally produced. Any earlier time, the universe would not have been transparent. So with light alone, we can't directly look any further back than this point where that cosmic microwave background light was produced. So with this light, we can't see any further back than the time the cosmic microwave background light was produced. Because before then, the universe would have been opaque. Light wouldn't have been able to freely move through the universe at any of those earlier times. So at least with light, we can only directly see back to that cosmic microwave background last scattering event. It's kind of like looking upwards and looking at a cloud. We can see through all of the transparent air, but once we hit the cloud, which is opaque, all those little, suspended water droplets that make up that cloud, that is opaque to visible light. We can only see back to that point where the cloud becomes opaque. Any further than that, we can't really see through that. So with light alone, we can't really see any further back than that transition from the era of nuclei to the era of atoms. Now, a couple of just side notes to this, a couple of expansion points on this. There could be events that happened earlier on in the universe that had an effect on the properties of the universe at this time and what sort of light would have been given off at that point. So in a sense, that last scattered light could encode some information about what the universe was like even earlier on. So we can still learn things indirectly about the earlier universe based on this CMB light, and we'll talk about that in a little bit later. But we can't directly detect with light alone. We can't directly observe what was going on earlier than this 380,000 year point between the era of nuclei and the era of atoms. There are other things that it may be possible to detect from earlier on. We'll talk about this a little bit later, like right at the end of the course, but gravitational waves, ripples in the curvature of space-time. We now have detectors that can measure the properties of gravitational waves. And gravitational waves can pass through pretty much anything. So if we can kind of quote unquote look at the sky in gravitational waves, it could be possible to see gravitational waves that were produced much, much earlier on, possibly all the way back to the GUT era. This is a possibility that is currently being explored. And if we're able to measure the properties of the gravitational wave background rather than the cosmic microwave background, we might be able to see effects from extremely, extremely early on in the universe. It's a very exciting new observational field. But let's get back to this cosmic microwave background. So in the 60s, in the 1960s, the early 1960s, there was still a lot of disagreement between scientists, astronomers, cosmologists, as to whether the Big Bang model was correct. There were competing models, for example, the steady state model, where as the universe expands, more material spontaneously is produced. And that's enough to kind of keep the universe just going through this kind of motion forever. So it never had any beginning. So yeah, there were other models that were being proposed for how the early universe would have acted. But there were a group of astronomers working on this kind of Big Bang timeline and identifying, well, if the Big Bang happened, if the universe were smaller in the past, we would have had this hot, dense state, and at some point, the universe would have been transparent, and then the universe would have become opaque. So they were kind of trying to figure out what would be the properties of this background radiation. What wavelengths should it be at? They were starting to predict that, oh, the temperature of this light now should be around 3 Kelvin, just a few Kelvin. And they were working on this, I think, there was a group at Princeton working on this in the early 1960s. At the same time, two scientists, Robert Wilson and Arno Penzias, were working at Bell Labs trying to make a microwave telescope, a telescope that didn't look at visible light, but was specifically designed to look at microwaves. They had different ideas in mind, and they were just setting up this telescope. And at the time, they were starting to measure some of the properties of this telescope. They were trying to calibrate it. And try as they might, wherever they aimed the telescope on the sky, they kept getting the same extra radiation that they were not expecting. Now, this was a sophisticated device. They had to identify all the sources of noise. The temperature of the telescope itself causes a kind of interference. So they were trying to figure out what this extra background light was coming from. They carefully checked every single rivet in the telescope, trying to make sure that nothing was reflecting some light in some weird way. They were trying to account for all of the different temperature parts of the telescope. They even were checking to make sure that there wasn't bird crap in the telescope, because that extra bird crap could cause a thermal signature that would throw off the measurements of the telescope. But no matter what they tried, they were still getting this extra radiation. So they called up their astronomer friends down the road, the ones who were working on this Big Bang model, and basically asked, we have this new microwave telescope and we keep getting this background radiation. Do you guys have any idea on what that might be? Which was exactly what the group of scientists were just starting to say, okay, how are we going to develop a telescope to make this observation, this groundbreaking observation? And Wilson and Penzias were actually the first ones to discover it. We can debate whether who deserved the recognition for the discovery more. Wilson and Penzias, who were the first ones to actually detect the light itself, or the group of astronomers that were the ones figuring out that the Big Bang should produce this kind of light, so let's go out and look for it. Again, I don't want to minimize either of their accomplishments. They were both groups were, great scientists doing amazing work. But Wilson and Penzias were the ones that got the majority of the recognition, including a Nobel Prize out of it. So what was the radiation that they saw? This is not quite the data that they saw. This is from a follow-up observation of the background radiation. And this is the intensity of that light versus the wavelength. The circles are the measurements of how much of this background light is at each of these different wavelengths. Notice this is in centimeters. And the solid line is what we would get from a thermal spectrum. remember that from Wien's law, for a thermal spectrum, we should be able to figure out the temperature by having this 2.9 million divided by the wavelength in nanometers. So let's try this measurement real quick. So if we have this radiation where it peaks, seems to be around just a little under 0.11 centimeters. So maybe let's call that 0.109 centimeters for the wavelength. In order to use the equation, we have to translate that into nanometers. So this lambda max in nanometers would be about 1,090,000. If we use this as 0.109 centimeters. Again, it's probably a little bit different than that. So let's take that value in nanometers, pause the video for a moment, and try to use Wien's law to calculate what is the temperature of this source. So pause the video, take a minute to do that, and let's see what we get. Okay, so again, if we have this wavelength in nanometers, to find the temperature, we do 2.9 million divided by that wavelength in nanometers. So if I do 2.9 million divided by 1,090,000, I get about 2.66. So I get a temperature of around 2.66 Kelvin. Again, this is a very low temperature. It's probably a little bit off of the actual measurement. Again, exactly finding where that wavelength is going to be a little bit difficult. The data that's given here is matching that with about 2.73 Kelvin. This spectrum that we're looking at, when we talked about thermal spectras earlier in the course, we said the thermal spectras approximately match ordinary objects. When we've looked at the spectras of stars, we typically have some other absorption features. There are usually some kinds of skewing of that spectrum, not quite following this exact black body spectrum. What we are seeing here is the most perfect thermal spectrum that we've ever seen in nature. This is very, very close to a perfect thermal spectrum. So it's almost a perfect thermal spectrum. Very, very few other features showing up in this spectrum. There are a couple in there based on what would have happened to that light after being produced by that transition from the era of nuclei to the era of atoms, and some other very, very tiny features that happens in a little bit of that cosmic microwave background light, but it's as close as we've ever seen to a perfect thermal spectrum. And one of the reasons for this is because when we talk about good thermal emitters, things that are very, very close to being perfect thermal emitters, the best ones are where there is no other ways for energy to either be added to the system or energy to be removed from the system. So if I have a dark piece of charcoal that's very, very dark in color, then it's going to be able to absorb and emit energy equally. It doesn't have any colors to it that are going to preferentially change some of those wavelengths. There's no other ways for that thing to either gain or get rid of energy, just using that thermal spectrum. If this light came from the entire universe, well, then there's not really any other ways for this thing to either absorb or get rid of energy other than through this radiation. The fact that we have this almost perfect thermal spectrum means this is not coming from some combination of stars, so not coming from a combination of stars or gas, clouds, because those would show different temperatures. There would be a superposition of objects of different temperature. They would have other kinds of spectral features. This radiation must have been coming from the entire universe as a whole. It is the leftover light from that cosmic microwave background, from that Big Bang event. So for this discovery in 1978, Penzias and Wilson were awarded the Nobel Prize in physics for being able to identify this leftover afterglow of the Big Bang, which, as I mentioned, this was the huge success in saying we have a prediction. Going from this era of nuclei to this era of atoms, we should be producing, when the universe becomes transparent, that light can now freely travel through the universe. It should be only a few degrees above absolute zero, so only a few Kelvin, and it should be coming from everywhere in the sky almost equally. So that confirmation was, again, what really in the scientific community gave very, very strong support to the Big Bang model, and they were awarded the Nobel Prize for it. What they also did was took their microwave telescope, and aimed it across the sky, kind of scanned across the sky to map out what this radiation looks like across the sky. And when they did that, they got the following graph. This is the map of the cosmic microwave background that Penzias and Wilson identified in 1965, where different colors represent different temperatures. So yeah, pretty much a constant temperature across the sky, at least to the level of accuracy that they were able to measure. So let's talk about this one for a second. Does this map satisfy the cosmological principle? Again, the cosmological principle being that the universe is homogeneous, no special locations, and isotropic, no special directions. So does this map seem to satisfy no special locations, no special directions? Yeah, it's basically constant across the entire sky. No special locations, no special directions. So the CMB light satisfies the cosmological principle. But does this lead to any questions? Pause the video for a second and think about this. If the universe, at the end of this era of nuclei, were perfectly uniform, without any variation at all, which is what this graph suggests, does that raise any questions? So pause the video for a second, think about that, and then restart. So if the universe were perfectly uniform, then, and there were no discrepancies, no denser regions, no less dense regions, if the universe were absolutely perfectly uniform, how did we end up with galaxies and stars and clusters of galaxies? Because the universe now is clearly not perfectly uniform. For example, I'm here and there's some empty space with air over here. Right below me, there's a planet. Other parts in space, there are not planets. So if it was perfectly uniform, how would we get any stars forming? We need some kind of differences where there are slightly denser regions that are going to collapse under gravity and start forming the seeds of galaxy clusters. Well, we need a better map then. So in 1992, there was a satellite mission called the COBE mission. I think it stands for Cosmic Background Emissions, or something like that. I might have that acronym a little bit wrong. But they were looking, using a satellite, to map out that microwave background radiation, and doing so to a higher degree of accuracy. So in this, now we have the general temperature, which is almost the same across the sky, but we get these tiny, tiny temperature variations going from hotter with the red sections and colder with the blue sections. So on large scales, let me just kind of mention this. On large scales, it looks the same. The CMB looks the same. On smaller scales, there's slightly hotter and colder regions corresponding to slightly higher and lower density regions. So there's small temperature fluctuations corresponding to tiny density fluctuations. So this COBE data from 1992, that shows where we have regions that there's slightly more material and slightly less material. It corresponds with these little temperature differences. And for that, and these are literally the seeds of the large scale structure of the universe. This is a baby picture of our universe. And those slightly denser regions, those are going to collapse under gravity and start forming clusters and superclusters of galaxies. So for this, the scientists for the COBE project were awarded the 2006 Nobel Prize in Physics. And since then, we've actually had a couple more missions mapping out this cosmic microwave background to ever increasing levels of detail. There was another one in between here, the WMAP experiment that released its data in, I think, 2003. And the most recent mission was the Planck mission that has been able to map out those tiny little temperature fluctuations to ever increasing detail. And there is a huge amount of information encoded in this cosmic microwave background. Based on the temperature of these of this map, we can use that as another way of figuring out what is the age of the universe. Based on the size of these fluctuations, both how large they are in the sky and how much of a temperature fluctuation there is, we can measure other properties of the very early universe. There is a huge amount of information encoded in this. So just to kind of finish up this, this cosmic microwave background, this leftover light from the cosmic microwave background is almost uniform across the sky, suggesting that it came from everywhere in the universe at once. It matches the predicted properties that we would expect from the universe going from this opaque state in the era of nuclei to this transparent state in the era of atoms. And these little temperature differences that we get, those correspond to the tiny little density differences in the universe, where we had this universe that was almost uniform, but with certain regions that are slightly higher density and slightly lower density. And those are the seeds of the large-scale structure formation. So in the next session, we'll talk a little bit more about this cosmic microwave background, some of the open questions about it, some ideas about inflation and ways to answer those. We'll play around with those in the next session.